So if you do have any questions, feel free to type them in the lecture text thread. I'll be reading that on my phone if I see anything coming up there. But we want to pick up, I guess, where we left off on Tuesday, talking about elimination reactions. We were in the midst of a discussion about the E2 mechanism. So we said the E2 mechanism requires a proton to be picked off from the beta carbon, one away from where the leaving group's located. And to typically promote that, we would use a strong base, one that is fully negative and will readily attack that proton, so these electrons can be pushed in and push out the leaving group. And so if I form the double bond here, I can imagine this product forming. But I could also imagine this bond rotating. I could at least hypothesize that rotation occurring and then doing the same mechanism, pushing out the bromine. And when the double bond forms, if the ethyl and methyl group are on the same side, I get a different product. So if we want to understand and be able to correctly predict which product is going to be produced, we need to look as closely as possible at this mechanism and at the spatial positioning of the groups, including the proton that's removed and the leaving group that's leaving, as well as the other groups and where they end up. So in this situation here, rotating this so that the two groups that are somewhat sterically hindering are on the same side, creating steric hindrance and repulsion in the product, that makes the product less stable and less thermodynamically favored. But since it's all happening in one step in the mechanism, the transition state for that is also less stable, right? So even during the transition state, where the bromine and the hydrogen are being removed and the pi bond starts to form, if these two rotate close enough to start causing repulsion, it's going to be less stable. So that pathway is not favored kinetically, and it's not favored thermodynamically, because it goes through a higher energy transition state, and the product is higher in energy or less stable due to the repulsion between those groups. So we do want to look at this in a little bit more detail, though. So let's take a look at another example. We can illustrate the difference between something that's stereoselective and something that's stereospecific. So here we're talking about stereoselectivity. So there's a minor difference between the steric repulsion here versus less steric repulsion here. So both these pathways are kind of similar in energy. So most of the molecules go through the lower energy pathway, but a few, if they undergo strong enough collisions, might go through the higher energy pathway. So I'm going to get a mixture of both. So it's selective in that I get one preferentially over the other, but it's not specific because I am actually going to get a mixture of both of these substances. Sometimes a process, though, is specific, which means stereospecific, which means it only happens in one specific way. The other option cannot form. And so let's take a look at an example of that. So when we look at this structure here, I've got my leaving group. This is my alpha carbon. And I only have one beta hydrogen, right? So I'm looking at the alpha carbon where the leaving group's going to leave. On this neighboring carbon, there's no hydrogens. On this neighboring carbon, there's one hydrogen. So if you did this experiment with this structure, which you could buy and run the reaction on and add a strong base, you would notice that the base, when it picks off this proton and electrons swing in and push out the leaving group, it produces only one product. There are two products you could imagine forming, but only one forms. And that product looks like this, right? So I'm forming the double bond there. I've got this aromatic ring here. I've got this methyl group here on the same carbon that the aromatic ring's on. The proton's gone, right? Its electrons are now in here as the pi bond. On the other carbon, I have a hydrogen, and I have a terbutyl group. I could imagine the other diastereomer of that or stereoisomer of that forming, where the terp butyl group ends up on the same side as the aromatic ring and the hydrogen's over here, right? If I prioritize these two groups, this is my top priority group. Prioritizing these two groups, this is my top priority group. So when the top priority groups are on the same side, that's Z. When the top priority groups are on opposite sides, that's E. So if I did this reaction, you might hypothesize that because of the sterics here, I would get less of the Z. Not many molecules would be able to go through the transition state or form the product where there's some steric hindrance between these larger groups. So maybe I would only get like 10% of the molecules forming this and most of the others forming the other one. But in reality, when you do this experiment, you don't get this one at all. And so that kind of surprised some chemists initially. And so they needed to look at this in a little bit more detail. And once molecular orbital theory was developed, there's a good explanation for this that we're going to go through right now and try to discuss. So in this particular case, the only one observed was the E, and that suggests that somehow the transition state that would have formed the other structure was a lot higher in energy, so much higher in energy than the other transition state that the structure just never formed. And so we want to look at those two possible transition states and look at the energies of them to try to explain this. So is this the favored product and I'm only forming it over the other one because there's only a slight difference in the transition states? No. There must be a big difference in the transition states if one pathway doesn't really produce a significant amount of product at all. Right? So if it's stereospecific and there's only one product specifically produced, one stereoisomer, in this case the E, rather than the Z, that implies that there's a big difference in the energies of the transition states between the two options. So what some chemists realized when they were looking more closely at molecular orbital theory was that in order for the E2 to occur, where the base picks off the proton and these electrons swing in and push out the leaving group, in order for that to occur all in one step, the orbitals all have to be in the same plane. Right, so what's going to happen here is I can imagine during the transition state, I'll put the bromine and the hydrogen in the same plane as the screen. And the base is going to come in on that plane. And so as this sigma bond breaks, and this sigma bond breaks, what's going to happen is those electron pairs are going to shift over a little bit, and we're going to form orbitals instead. In order for this all to happen at one moment, those orbitals that were forming sigma bonds that are going to become pi bonds, they have to be in the same plane. There isn't time for the carbon-carbon bond to rotate. So whatever electrons are going to come in here and form this pi bond, and whatever orbitals previously existed, they have to be in the same plane that the new p orbitals are going to form in as they overlap side by side. Because it's all happening in an instant. It's all happening in one moment. There isn't any time for the carbon-carbon bond to rotate. So that means they have to be coplanar, meaning the leaving group and the hydrogen have to be in the same plane in order to convert the orbitals that were previously existing in these sigma bonds into the new pi p orbitals. They're going to create the pi bonds. So since we know the orbitals all have to be in the same plane in order for them to transform from sigma bonds to pi bonds, there are really two options we could imagine for the transition state and the geometry that occurs. Right? There are two coplanar options. One is anti, where the proton and the leaving group are anti to one another. That's 180 degrees dihedral angle. So if you recall when we talked about Newman projections, if we looked at this as the front carbon here, the hydrogen would be coming down, not really drawing all the other groups in, just focusing on the hydrogen and the leaving group. The back carbon behind there the bromine would be pointing up, right? So that's anti, 180 degree dihedral angle. It puts them in the same plane. The other option for them to be in the same plane would be what's called syn, which means they're on the same side. So it's similar to cis, and this is similar to trans, but the terms syn and anti refer to a situation where it's a single bond and it could rotate. Cis and trans refer to a situation where it's a double bond and it can't rotate. So if I do the same thing here and imagine myself looking down this angle, the front carbon would have a hydrogen pointing up, and the back carbon would have the bromine pointing up. So here they'd be eclipsing. Either way, as long as they're in the same plane, their sigma bond orbitals can be converted to p orbitals, and they'll be already in the same plane, ready to overlap side by side to make the pi bond. So either of those is reasonable. But what we'll observe is this form here does not produce the product. And the reason for that is because the other eclipsing groups cause too much torsional strain, and that makes it way higher in energy, so none of the collisions really have the energy necessary to go through that transition state. So why does it proceed through the anti-coplanar structure only? Well, it has to do with where the other groups are. Right? So I'm going to call this ring a pH for phenyl. It's a phenyl substituent, just to make things a little easier. And I'm going to call this a terbutyl. So let's look at where these are. So if I'm looking down this bond here, the solid wedge is pointing to my right. So off the front carbon, I'd have the phenyl group here and the methyl group back here. And off the back carbon, I'd have the hydrogen on my right and the terbutyl group over here. So all the groups are staggered. And during that transition state, where the base picks off this proton and the leaving group leaves, all of the action for the electron movements happening in the same plane. So those orbitals can convert from sigma orbitals to p orbitals and form the pi bond. And as that's happening during that moment, it goes through a relatively low energy transition state because all the other groups are staggered and there's no repulsion due to eclipsing groups, which is also known as torsional strain. Alternatively, if I eclipse the hydrogen and the bromine to get them in the same plane, so their sigma bonds are in the same plane and they can be converted into p orbitals and form that pi bond in that plane, what would the rest of the groups be doing? Well, I would have on the front carbon the methyl group coming down to my right. I'd have the phenyl ring coming down to my left. Since it's behind the plane, I'm looking in this angle. On the back carbon, the hydrogen would be coming down to my right, and this terbutyl group would be pointing down behind. So really, even though these are big groups and they create extra repulsion, anytime a carbon-carbon bond rotates into this position where all the groups are eclipsing, it's going to be really unstable. So that option 2, would go through a much higher energy transition state. Even though the product would be similar in stability, the transition state is so much higher, it just doesn't occur. So we don't really see elimination by this mechanism occurring through transition states that involve eclipsing. And what that means is you won't be able to remove a hydrogen at the base and kick out a leaving group if they're syn. They have to be anti. The leaving group and hydrogen have to be rotationally, in terms of their torsional angle, 180 degrees in order to avoid the eclipsing and go through the stable enough transition state to make the process feasible. And so that's also demonstrated over here, same exact thing. So since this is the only structure that puts the two groups, the leaving group and the hydrogen, in the same plane, but also avoids torsional strain, the transition state is going to lock this into place. As this sigma bond breaks, and this sigma bond breaks, and they both get converted into p orbitals in the same plane to form that double bond, there's no time for the front carbon, back carbon bond to rotate. And so the pH and the H are locked in on the same side of the double bond that forms. There's no time for it to rotate and get the hydrogen and the phenyl group on opposite sides of the double bond, and likewise the methyl and the terp-butyl are locked in on the same side, because as the sigma bonds get converted into pi bonds, there's no rotation. It's an instantaneous one-step mechanism, and the transition state forms and reacts immediately. There's no time for rotation to occur during the transition state, and so the methyl and the terp-butyl group also end up on the same side. So you have to make sure that you understand this, because it's really the only way to correctly predict the stereochemical outcome at this pi bond. Right? So in this case, I'm forming the E configuration. I'm not forming the Z. And the only way to be sure to recognize that is to understand that the leaving group and the hydrogen have to be anti to one another, and that will lock in certain groups on the same side of the double bond when the double bond forms. So some other evidence after that suggested that it doesn't have to be exactly anti with an exactly 180 degree dihedral angle. There's some deviation that's okay. So they adjusted the term. Instead of anti-coplanar, it's actually called antiperiplanar, right? So if the front carbon, maybe the atom is straight up, the back carbon, instead of pointing straight down, maybe it's like slightly down at an angle. As long as they're close to 180 degrees, well, then those sigma bonds can be converted into p orbitals, and the p orbitals can overlap to create the pi bond. And so the term for that is antiperiplanar. So we'll be using that term throughout the rest of the discussion. Antiperiplanar just means that the hydrogen on the front carbon and the leaving group on the back carbon are approximately anti to one another, and that allows all the other groups to remain staggered, avoiding the unstable torsional strain during the transition state. It may lead to the less stable isomer in the end. So let's look at an example where that's the case. So let's say R1 here is a big crowded group, and R2 is a smaller group, like a methyl. So in this particular molecule here, if I have this big crowded group creating a big cloud of electrons, and they're both on the same side, that might cause some repulsion. So you might be tempted to avoid putting them on the same side of the double bond. But if they both have solid wedges, they're on the same side. Assuming they both have solid wedges when both the hydrogen and the bromine are anti to one another, that means those two large groups would be locked in on the same side of the double bond. So when the base comes in, picks up this proton, these electrons come here and push out the leaving group, that all happens at once. If it's a strong base and it's coming in right away and it's doing an E2 mechanism, the hydrogen and the bromine have to be anti during the collision. And that means any groups that are both solid wedges will end up on the same side of the double bond. And then obviously the groups with dash wedges would end up on the same side as well. And so even though these R groups might be sterically hindered, and it's not as stable as it would be if they were on opposite sides, this one just can't form from this original structure because there's no way to rotate them to opposite sides. If I rotated it to put the hydrogen and the bromine in the same plane, well, then this R group would rotate over here, and this R group would rotate into the front, and this one would remain because I didn't rotate that side of the bond. I could do the reaction through this structure, but since the R1 and R2 are actually eclipsing, it's even more unstable by a lot than it would be if they were staggered. So the Gauss interaction here, it might be a little bit unstable if there's some crowding, and it leads to the larger groups on the same side crowding on the double bond, but that's much more stable during the transition state than trying to eclipse groups on adjacent carbons. So I want to avoid the eclipsing and make sure that the hydrogen and the leaving group are not syn, but rather anti. So if I start with a different stereo isomer to begin with, once I rotate the hydrogen and the bromine anti to one another, if the two groups end up on the same side, in this case the R1 and R2 both have solid wedges, that would produce the product where they're on the same side. And obviously the R2 and R1, the two that both have dashed wedges, would end up on the same side as well. So starting with the specific configuration, knowing that the hydrogen and the bromine have to be anti, I can predict the stereochemical outcome, or which groups are pointing in space on which atoms in the product in both of these reactions. So let's look at this example here. What would be the product that would be produced? So this reaction is stereospecific. Actually, no, this one is stereoselective, right? So let's take a look at this. So in this case, there are two hydrogens on the beta carbon. So I have to recognize only the hydrogen that rotates into the same plane as the bromine, positioned anti, will be able to be removed by the base. But before that happens, this single bond here can rotate. So either one of those hydrogens could rotate into the plane. And so I have to look at both possibilities. So the hydrogen that's already in the plane with the bromine, if the base were to take off that and push these electrons in, and push that leaving group out, then this hydrogen and R3 both have dash wedges, so they would end up on the same side of the double bond. And R1 and R2 would end up on the same side of the double bond. If, however, the single bond rotated so that this hydrogen here were to come forward and get into the plane, the structure would also be able to do an elimination, because the other hydrogen would be anti-periplanar to the leaving group. So let's draw what that would look like. So in order to do that, I'm going to keep the right-hand side of the molecule the same. The bromine on the plane, R2 coming out at me, and R3 down here. I'm going to rotate the single bond so that this hydrogen that was pointing away rotates down and into the plane. So we'll call this H2 and this H1. So H2 is going to rotate down into the plane, where the other group's going to end up. What's coming from behind, so it's going to rotate here. So this hydrogen is then going to rotate up into a solid wedge position, and the R group is going to be pushed back into a dashed wedge position. It's much easier to see if you use a model. So I encourage you to make a model and rewind to this part of the video later and make sure that makes sense to you. So now that H2 is anti-periplanar to the bromine, the base could pick it off. So some of the molecules might rotate into this form, others might rotate into this form. So that's why I'm likely to get multiple products, and it's only selectively producing one over the other, not specifically producing one over the other. So if the base comes into H2, pushing electrons in, pushing out the bromine, that's going to give me the double bond. So now H1 is on the same side as R2, because they both have solid wedges. They're both pointing out at me. They end up on the same side of the double bond. And R1 and R3 both have dash wedges, so they're going to end up on the same side. So am I going to get equal quantities of these? Probably not. It depends on what R1, 2, and 3 are and how sterically hindering they are, right? So in the top structure, R1 and R2 are on the same side, and those are probably, R represents carbon groups, so those are carbon groups depending on how big and branched and bulky they are. That might be a little unstable. In the other structure, R1 is on the same side as R3. So if R2 is big and bulky, this will be less stable. So let's just make that presumption. Let's just say R2 is bigger than R3. In that case, I've got more sterics here between these two groups. It's going to be crowded. Here, it's less crowded. If R3 is smaller than R2, it's not going to be much steric hindrance there. So, since both of these can form through an intermediate where the hydrogen is antiperiplanar to the leaving group, they will both form. That is the main thing. If you're going to do an E2, you have to get the hydrogen antiperiplanar to the leaving group. Once that occurs, then any groups that are solid wedges will end up on the same side. If they're crowded, it might be a slightly higher energy transition state, so I would get less of that. This would be a minor product, because the single bond would likely rotate into a position where the other hydrogen becomes antiperiplanar and gets picked off, if that prevents the largest groups from creating much sterics on the same side of the double bond. So if it's a little less crowded, it would be the major product. So when I get some of each product, that's selective. I'm selectively producing a little bit more of one than the other. Specific would be if only one of these forms and the other can't. But that's not the case here, because both of them can form from a different hydrogen getting into the antiperiplanar position with respect to the leaving group. So let's take a look at some examples where the leaving group is on a chair. What we see here, if we look at the Newman projection of this chair, is that if my leaving group is in an equatorial position, which it often will be because it might be bulky and that avoids some steric hindrance, if I put it in an equatorial position, that means the positions that are anti to it, or like 180 degrees pointing at a 180 degree rotation, are carbons. I don't have a proton. The protons are gauche. Right? This leaving group is gauche to the proton, and that's what I see here. The leaving groups on this carbon, the proton on the neighboring carbons are both gauche. So there's no way to do an E2 elimination when my leaving group's in an equatorial position. Only when the ring flips to put the leaving group in an axial position will there actually be protons in positions that are anti-periplanar to the leaving group. Right? So that's what we see here. This chlorine, and there's an anti-proton. So a base can pick that off, and the sigma bonds can become p orbitals, and pi bonds can form without requiring any rotation. So if you have a leaving group on a chair, and a strong base is added, suggesting that the base is going to come in right away and get a proton, it's not going to work when the leaving group is equatorial. It will only work when the ring flips and puts the leaving group in an axial position. So that has some consequences. We want to take a look at it in a little bit more detail. So, situation here. I want to draw a couple chairs for these structures. I want to recognize, if I'm imagining an E2, that I've got to put the leaving group in an axial position. So with a solid wedge, it's got to be up. So I don't want to put it here, up equatorial. I want to put it on one of these three carbons here. So it'll be up axial. So I'm just going to put it there. If it's up axial and the methyl groups are also up because they also have solid wedges, and then on the adjacent carbons the methyl groups would end up being up equatorial, and there'd be a hydrogen here or here. So in this particular structure, it's set up so that the leaving group and the hydrogens can be anti, and that will allow for the elimination to occur. Conversely, if I draw this structure here and I try to put the chlorine in the same position, specifically putting it in an axial position so that I can see if the neighboring carbons have axial hydrogens that are anti-periplanar to it, but when I look, the neighboring carbons have methyl groups in the down positions. Right? The dash wedge means down. So the down position on the neighboring carbons is occupied by methyl groups rather than hydrogens. The hydrogens here are in the equatorial positions. So these hydrogens are gauche. Their bonds are not in the same plane as the chlorine, so there's no way for the orbital overlap to occur properly to form pi bonds here. So this one cannot undergo E2. This one can, because a base could collide. If a base collided with either one of these hydrogens, it could shift electrons in and push out the chlorine, because the hydrogen and the chlorines are all in the same plane, and that would allow for the pi bond to form. Any questions about that? Alright, this is always tricky, so let's look at a couple more examples. So here I want to draw the possible products. If I give you a flat structure and you've got a leaving group and you're trying to imagine the possibility of doing an E2 elimination, in this case it's called dehydrohalonation because we're removing a hydrogen and a halogen. Right, that's an E2. Leaving group leaving, picking off a proton. So I want to first convert that into a chair so I can make sure that if the leaving group were positioned axial and I draw in the other groups, the methyl group would be down since it has a dash wedge. In this case, there's only one beta proton that could be picked off that's actually antiperiplanar to the leaving group. So my base would pick off this proton, these electrons would go in here and push out the leaving group. So the only product I would get would have the double bond over here and the methyl group down. And if I were to redraw that so the ring looks kind of flat again, wherever I make the pi bond, it would have to be on the other side. I need the hydrogen here that's anti to the chlorine to be picked off. And so the methyl group would remain there. And so that would be the only product I could make from that reactant. So even though there's a hydrogen here, there's no way for it to be anti to the chlorine, so it cannot be removed by the base, and I cannot get the pi bond on the other side. It's not going to be possible. So there are specific spatial limitations here you want to make sure you're aware of and can work through. So let's say we've got this structure. Here I want to look at the same option. So I want to put the chlorine with the solid wedge. I want it coming up, so I'll put it here again. So at least I have the possibility of something being anti to it, right? If I put the chlorine here in the equatorial position, anti to that, there's already carbon-carbon bonds, so there'd be no way to do any elimination at all if the leaving group were in an equatorial position. So I have to start with the leaving group in an axial position if I even want to entertain the possibility of an elimination. So then, if I were to number the carbons, carbon would be carbon 1, carbon 2 would be over here. Carbon 2 has a isopropyl group up, so the up position there is the equatorial one, which leaves the possibility for a hydrogen down. As I go around the ring, over here, I've got a methyl group on carbon 5 down, so that would also be equatorial. And so that's helpful. And if I try to imagine the ring flip here by pulling the feet of the ring up and pushing the head down, if this ring flips, this isopropyl group will end up being axial. And this methyl group over here will end up being axial. And so these two axial groups would majorly, especially the isopropyl group because it's so crowding, it would majorly collide with the other axial groups on the same side of the ring. That would be extremely unstable. So when this flipping occurs, it would flip immediately back. And so almost all my molecules would actually exist in the more stable chair, which actually puts the chlorine axial and antiperiplanar to this hydrogen as well as this one. So in this case, the base could collide at either one of these axial hydrogens and do the reaction. So I ran out of space here, so I'll do that reaction and show one of the products there and the other here. So if the base picks off this proton here and these electrons swing in, since it's anti to the chlorine, that's reasonable. That would prove by double bond there on that side between the carbon 1 and 6, and so that would look like this. So I would still have the isopropyl group pointing up at me and the methyl group pointing down. but then I would form the double bond here between 1 and 6. Alternatively, if the base picks off this hydrogen and these electrons swing in to push out the chlorine, I get the double bond on the other side between 1 and 2. So it's a different regiochemical outcome because I've got two different beta hydrogens that are both antiperiplanar to the leaving group, and either one could be picked off, just depends on where the base collides. So that would form my double bond here. Once I have a double bond, I don't have a solid or a dashed wedge anymore for this isopropyl group, because now this carbon is sp2 and it's flat. All the groups are in the same plane. This one is still sp3, and so it still has the dash wedge. So here I got two different products. What's the relationship between them? They're constitutional isomers. It's hard to control which one would form because there are two available hydrogens that the base could pick off that are both antiperiplanar to the leaving group. And then this third one, let's take a look at this one. So here I've got the chlorine with the dashed wedge. So when I draw my chair, I want to imagine it coming down. So I'd want to try to put it straight down, so at least there could be a hydrogen here or here that would be in the same plane that would be anti. But I don't know if there are hydrogens there or not. I got to look at the structure. So with this chlorine here, we'll put this in carbon 1, 2, 3, 4, 5, just to keep track of the carbon. So 1, 2. On carbon 2, there's actually an isopropyl group with an up. So this can't be where the hydrogen is. The isopropyl group is there. So that isopropyl group will be blocking that position. So I can't form a double bond there because I don't have a proton antiperiplanar to the leaving group. This proton is here though, which would be carbon 6, and then the methyl group would be on carbon 5. So I could imagine a base picking off the proton, pushing these electrons in, pushing out the leaving group, because the proton and the leaving group are antiperiplanar. As long as I use a strong base, it could collide there, and that could happen. And if that happened, I would form a double bond right here, right between the alpha and beta carbon. And if I redrew that, it would look something like this. Right, the isopropyl group would still have a solid wedge. There would be a double bond here, and then I'd have the methyl group with the dashed wedge. The problem with that is it would be extremely slow. Why would it be so slow? It looks fine. The problem is that this molecule is really unstable because there's a big bulky group in an axial position crowding out these other axial groups, even though they're hydrogens. Even if all three were hydrogens, it's still a little bit of crowding, but when I put a big methyl or even bigger isopropyl group in, it's a huge amount of crowding, makes it very unstable. So this ring, before the base would even have a chance to collide with this beta hydrogen, would probably very quickly undergo the ring flip. And the ring flip would be necessary because then that would allow the isopropyl group here to still be in the up position, but now be equatorial instead of axial. And that, however, would put the chlorine in an equatorial position, and it would also put this methyl group in an equatorial position. So with all my groups axial, it's way less stable, especially the isopropyl group. Much more stable in equatorial positions. And this flipping of the ring would greatly favor this substance that cannot undergo elimination. It cannot undergo elimination because there's no proton anti-periplanar to the leaving group. So only once in a great while would one of these actually exist in the other form, and when it does, it would require the base to come in and collide right away with that proton before it flips back to the other structure that's unreacted. And so that would be extremely slow, very slow, because only once in a while would a molecule exist in this form, and usually when it does, it would flip back to the other unreacted form before the base has a chance to come in. Right? So you would probably see this reaction appearing to be virtually unreactive due to the kinetics of it being so extremely slow. I think that does a pretty good job of illustrating that, so I think I'm going to just skip this slide over. No, it's too important. So here we have a fused ring system, so that means we've got two different rings fused together, two different chairs fused together. Right, so on this chair, I've got a dash wedge here, so the hydrogen's pointing up, and that would be this hydrogen here. On this carbon, I've got a solid wedge shown, so the hydrogen has a dash wedge, and it's right there. So my chlorine is over here. So if I were to number these carbons, 1, 2, 3, 4, 5, 6. Carbon 1 would be here, 2, 3, 4, 5, 6. So the chlorine is on 4 and it has a dashed wedge, so it would be down. The methyl group on 5 has a dashed wedge, it would be down. So the most stable version of this chair is fused chair system, looks like this. The methyl group's the bulkiest group here, and having it in equatorial position means I don't need to flip anything to make it more stable. So this is what most of the molecules would look like. So if I use this base here versus this base here, what's the difference? Well, the ethyl group is not as sterically hindering. So this isn't going to create as much steric when it comes in. The terp-butyl group, last time we said, it'll usually do the elimination at the side that's less sterically hindered. So when I look at the sterics here, first of all, I have to recognize when the chlorine is in an axial position, only the hydrogens on the very next carbons are antiperiplanar to that. So I've got two possible hydrogens that could be picked off by the base. And I want to consider what products would be produced from that. So when I have a very bulky base, even though it's strong because it's negative and it needs to pick up a proton, it's probably going to go for the proton with the less sterically hindered stuff going on. So here I've got more carbons attached, and I've got the other fused ring. There's a lot more steric hindrance over here due to the larger electron clouds. So this probably would be a large enough cloud to avoid coming into this hydrogen over here. It'd be more likely to get this one, push these electrons in, and push out the chlorine. So that would give me a product that would form the double bond between the chlorine and carbon 3, or between carbon 4 and carbon 3. Crap, let me redraw that. So I would have the double bond between 3 and 4, and the methyl group would still be here. So that would be the major product that we get with a more bulky base. And so the bulky base affects the regioselectivity. Which hydrogen, if I've got more than one hydrogen that's antiperiplanar to the chlorine, the bulky base will go for the one that's got less sterics around it. The less bulky base could go to either side. There's no reason why this oxygen with the smaller group attached wouldn't be able to access both hydrogens. And if it can access both, the one that will go through the lower energy transition state and form more often will be the one where when the double bond forms, it's a more substituted double bond. So this double bond has a couple hydrogens. If I pick off the other proton and form the double bond between 5 and 6, there aren't any hydrogens there. I'm sorry, not between 5 and 6. I apologize. Between 4 and 5. There aren't any hydrogens there. Other than the hydrogen that's on 4. But there's no hydrogens on 5 compared to 3, right? So what we're talking about here is getting this hydrogen versus this one. And when I have a less bulky base, it can pick off either one of those. It's going to pick off this one because during the transition state, as the pi bond starts to form, it's more substituted with the extra carbon group versus with the extra hydrogen. And the more substituted with carbons the double bond is, the more stable it is. We saw that last time. The more readily it will form. So I expect this base to come in here and pick off this proton to push the electrons in and push out the chlorine. And so that would produce a different regiochemical outcome. So I'm not changing the fused ring system. I'm forming the double bond on the other side, which would be here. And now that methyl group is in the plane because it's no longer sp3 hybridized. So I get the double bond over here if I use the bulkier base because there's less sterics. I get it over here if I use the less bulky base because as it forms, it's more substituted with the extra carbon group, and that helps to stabilize it during the transition state and also as a product. And so that product would be both kinetically and thermodynamically favored with the smaller base. Whereas this product, even though it's not thermodynamically favored because the double bond's not as stable as the other one being less substituted with carbons, it would be kinetically favored because it would go through a lower energy transition state to avoid the sterics between this large crowded group and all the stuff happening over around this hydrogen. Alright, so that leads us to the first quiz question. What am I seeing here? I'm seeing a strong base. If it's strong, it suggests it's going to be an E2. But at the moment, my chair is not set up for an E2 because the bromine is equatorial and there's no antiperiplanar hydrogen. Right? The groups that are anti to this are this group, and neither of those are hydrogens. They're both carbons. So before the E2 can happen, this would have to flip into the opposite chair conformation so that the leaving group can actually get into an axial position. So it's slightly down, which means it's still going to be down. But when the flip occurs, the equatorial becomes axial, still down. And that means this axial down becomes equatorial down. This equatorial up becomes axial up. And this equatorial up becomes axial up. And that's unfortunate. So which of these two is favored in the flip? Well, the original is slightly favored, right? Because I've got 3 equatorial groups and only 1 axial. Here I've got 3 axial groups and 1 equatorial. So unfortunately, this is going to be a slow process. Most of the molecules will exist in this form that can't react by an E2. Only once in a while will one exist in this form. And when it does, there's only one hydrogen that's anti to the leaving group. This is a methyl group. It's this one right here. And so there's no hydrogen that's anti to the bromine on that carbon. The only anti-hydrogen is on this carbon. So even though this might be slow because most of the molecules wouldn't exist in the reactive form, the advantage here is it would be stereospecific. There's only one stereochemical and also regiospecific. There's only one region where the reaction can occur. That's this hydrogen. And there's only one product that can form because there's only one rotation where the hydrogen can actually get antiperiplanar to the bromine. So if the base picks off this hydrogen and these electrons moved in here, now push the bromine out, that would produce a structure that would look like this. So this carbon would still be equatorial. I would form a double bond here, and I would still have this carbon here. And so if I drew that flat, I would have the double bond here between this carbon and this carbon, where the hydrogen was actually anti to the bromine. There's a methyl group here, and then there's a methyl group here with a solid wedge because it's pointing up, as well as the methyl group over here that has a solid wedge because it's also pointing up. So there'll only be one product in this reaction as a result of there only being one hydrogen that can get antiperiplanar to the leaving group. Questions about that? Alright, so that's a pretty detailed look at the E2 mechanism. There's a lot there for you to practice. So we're going to transition, talk a little bit more detail about the E1 mechanism. As we said before, the E1 is a two-step process. The reason it's called E1 is because it is first order overall. The only substance that affects the rate is the substrate. And that's the same as in the SN1, and for the same reason, right? We said the SN1 and E1 go through the same first step. The first step of their mechanism, I mean, there may be a proton transfer that occurs before that possibly, but the first step that is actually part of what defines this mechanism is the loss of the leaving group to produce a carbocation. So the same rules we talked about for the SN1 in terms of when we can and can't form a carbocation due to its stability apply here. So the leaving group will only be able to leave if it's a secondary or tertiary carbocation, or if the carbocation is stabilized by resonance. But if that occurs, then there's two possible things that could, well, first before I mention that, this is a slow step. Forming a carbocation is not easy. It takes a lot of energy. And so this would go through a pretty high energy transition state. So really the rate of production really only depends on however often the carbocation can form. And that depends on the quality of the leaving group and the stability of the carbocation and how well the solvent facilitates the loss of the leaving group and stabilizes the transition state during it leaving. So if the leaving group leaving first is the slow step, only this substance is involved in the collision during that step. So that's why having more of it would facilitate more collisions and increase the rate. Having less of it would have less collisions and the rate would, I wouldn't get as many product forming per second. But the base is not involved in that because it's coming in quickly afterward to finish the process off. What's slowing the process down is the first step, so only collisions that occur in the first step affect the overall rate. Once the carbocation is formed, we could easily imagine the base picking off the beta proton. If there are multiple beta protons, it could pick off any one of them. At this point, there's no requirement for things to be antiperiplanar because the leaving group's already gone. So any beta carbon that's one away from the carbocation, that has a hydrogen, that hydrogen could potentially rotate into position overlapping its sigma bond with the p orbital, the empty p orbital, so that when the base picks up that proton, this carbon can rehybridize and make a p orbital without rotating the bond, and then those orbitals can overlap to make the pi bond. So the pi bond could happen any side here. In the case of the symmetrical structure, I get the same molecule either way, right? If I drew it like this, obviously those two are the same structure, just rotated differently. So there's some specifics about the E1 here. The kinetics only depend on the substrate. And once the carbocation is formed, we don't have to worry about antiperiplanar. Any beta hydrogen could potentially be picked off by the base. We also want to consider the fact that bases and nucleophiles have a lot in common. Whether it's a nucleophile or a base, they both have a lone pair of electrons. They often both have a negative charge. They both are trying to share those electrons with something to balance out their charge. A nucleophile, though, attacks the carbon. So nucleophile is going to be something that is more stable sharing electrons with carbon, while a base is going to be something that's more stable sharing electrons with a proton. And so a little later we're going to see what some of the differences are and how to know which is going to occur. If I have a nucleophile around, it might go right into the carbocation, do substitution. If I have a base around, it's more likely to pick off the beta proton and make a pi bond, completing the elimination. So we'll talk more in detail about how to tell what's happening when, after we talk about the mechanism a little bit more. So just to point out, we said this is an E1, it's first order overall because the substrate is first order. But what if the second order, what if the second step were the slow step? So we know that the loss of the carbocation, the loss of the leaving group to produce the carbocation is the slow step. The second step is fast in comparison. If, though, the first step were the faster step and the second step reached a higher energy transition state than the first, then the second step would be a slow step. And what would matter would be how often the base and the intermediate collide. So then the rate would be dependent upon the amount of base. The more base I put in, the more often it would collide with the intermediate, and the faster the product would be produced. So the fact that I can show experimentally that when I put in more base, more moles of base or less moles of base, it doesn't affect the rate, tells me that the base is zero order, and that tells me for sure that the base is not involved in a collision in the slow step. So I know for sure that this is not what we're dealing with. We're dealing with the first step being the slow step because the base is actually experimentally verified to be zero order. So for the same reason we said E1 has this reactivity trend, SN1, E1 has the same reactivity trend. And hopefully that makes sense to you. We already said how if a leaving group leaves a primary carbon, that is too slow to even measure because the primary carbocation is so unstable. This one would go through a really high energy transition state, and so it really happens so slowly, it's immeasurably slow. If a secondary leaving group leaves, it starts to form a carbocation here. It can be stabilized by induction and hyperconjugation a little bit more, and if it leaves here, even more carbon groups to push electrons in through induction and to rotate a CH bond into the same plane as the p orbital to share electron density through hyperconjugation. So we expect, since the loss of the leaving group is a slow step, the more stable the carbocation is that forms in that step, the more often the step will occur. Right? So we see the same energy differences we saw when we were talking about the SN1. So this is exactly the same as we saw in Chapter 7. The SN1 and E1 both go through the same slow step, so their kinetics are pretty much identical. During the transition state, if it's secondary, the leaving group starts to leave, and I start to produce some positive here and negative here. There's some induction here to shift some electron density in there, and there's some hyperconjugation for this sigma to get into the same plane as the orbital that's to form and donate some electron density in to stabilize that partial positive. So the transition state here is low enough for it actually to form once in a while, but when it's tertiary, well, not to make a dotted line there, I'll do it up here. When it's tertiary and the leaving group starts to leave behind a positive charge during the transition state, the extra induction of the carbon-carbon bonds shifting electrons into to stabilize that positive, and the hyperconjugation of the neighboring CH sigma bonds rotating into the same plane as the forming p orbital, donating some electron density to stabilize that positive. That stabilizes the transition state, so it happens more often, and that's why we see orders of magnitude faster reaction rates with the tertiary substrate through both an E1 and an SN1 compared to the secondary substrate. So make sure that you can explain. A lot of students have been having trouble explaining the hyperconjugation and induction with those E1 and SN1 mechanisms. So as we were saying, once the carbocation forms, that's the slow step, right? So this is the slow step. This is what determines the rate. What determines the actual product that's formed, though, that's determined by whether the nucleophile comes all the way in to form a new sigma bond, or whether it acts as a base to pick off a proton to form a new pi bond. So there's some advantages, or I should say there's some details we can take advantage of to try to force the reaction to produce one or the other. We're going to talk about those a little bit throughout the rest of the discussion. So one is making sure that we don't really have anything nucleophilic around. So we have to look at some examples of some substances that are willing to pick up a proton but that are less willing to act as a nucleophile. Another point here is that when the base picks up this proton, it remains as a separate molecule from the product, versus when the nucleophile attacks, it connects here and forms one substance. So if I do create an equilibrium where this is all in equilibrium together, thermodynamically, if I increase the temperature, it's not like it's facilitating this collision more often than the other, but due to entropy, if my reaction produces 2 moles of products versus 1, the extra substance has more variety in entropy. So when I do the elimination, the entropy change is going to be positive. And so increasing the temperature will make this negative term larger, and it will make that process more spontaneous, making delta G more negative. So if you have a competition going on here, and when the nucleophile comes in, it can also leave and go back to the carbocation, and when the base picks off the proton, the pi bond could pick that base back up, and so that could also go back. If it can keep going back and forth and shifting back and forth, when it gets to equilibrium, I can control it to an extent. I can increase the temperature, which will make this specific pathway more significant because of the more negative sign for delta G that's created at a higher temperature when I have a positive value for delta S. We'll talk more about that later as we go through the discussion. So as we were saying in the SN2 and SN1 and E2 reactions that we looked at before, a lot of times you have an alcohol as your molecule, right? An alcohol just has an OH attached to some carbon group. It's not a good leaving group though, so we talked about how to use an acid to make it a better leaving group, right? So some of our strong acids, we could use HCl, HBr, HI, H2SO4. Well, these strong acids will promote a proton being picked up to make a water leaving group, and then the water leaving group could leave, and now we get a carbocation. But with any one of these acids, X is either going to be a Cl, a Br, or an I. And each one of those with a negative charge and 4 lone pairs is somewhat nucleophilic. So usually I get a substitution. So here's one detail. If I want to replace an OH with a halide, I can use HCl, HBr, or HI, right? The proton will be picked up by the oxygen, the water leaving group will leave, and then the Cl, Br, or I would come in to make a new sigma bond. So if I want to do a substitution, these are the 3 bases that I would probably be looking at, acids I would probably be looking at. If I want to do an elimination though, sulfuric acid is a great option, or phosphoric acid. You see that one as well. And the advantage there is when the oxygen picks up a proton from sulfuric acid or from phosphoric acid, the resulting conjugate base is not very nucleophilic. And so that promotes the elimination. So let's look at that mechanism and talk about that a little bit. So we'll come back and do those other 2 in a minute. I just want to show you the mechanism first. So if I'm going to treat this with concentrated sulfuric acid, in a minute we'll see why it has to be concentrated, but the sulfuric acid in water, we know this reaction from general chemistry, sulfuric acid is a strong acid. So the water is going to pick up a proton, these electrons will stay behind, so I'm going to get H3O plus and HSO4 minus. The HSO4 minus is the key. It's non-nucleophilic. And that's because it's, I ran out of space there, non-nucleophilic. That's because it's such a great leaving group. It's an even better leaving group than a chloride, bromide, or iodide. It doesn't form a very good bond with carbon. So I'm introducing the extra H3O plus, and this HSO4 is nothing. It's just a spectator. Once it forms, it's not going to react in any way. So using sulfuric acid in water or phosphoric acid, basically I get H3O plus and something that's non-reactive. So what's going to happen here in the mechanism is the oxygen is going to pick up a proton. These electrons will stay behind to balance the charge on that oxygen. So that makes a water leaving group. Now my water leaving group is attached to a tertiary carbon, so I do expect it to leave. because the resulting carbocation is not terribly unstable. Once the water leaving group leaves, the carbocation is now flat. So I don't have a dashed wedge here anymore. Dashed and solid wedges only belong on sp3 hybridized carbons. An sp2 hybridized carbon with an empty p orbital is going to be flat. Once that forms, I don't have a nucleophile around, really. I mean, what's the best nucleophile around? Water. That's my solvent. It's concentrated, so there isn't much water. Plus, I had a water leaving group here. So I could imagine a water coming back into the carbocation that would just go back. But then if it left again, I'd reform the carbocation. So this could easily form an equilibrium. And this first step would be an equilibrium as well. Instead, though, the water could pick off a beta proton. And so there's one here, there's one here, and there's one here. So which one makes the most sense? Well, whichever goes through a lower energy transition state and or forms a more stable product, that should be the one that happens more often. So when we're looking at forming a pi bond, we want to form it between carbons that have the most carbons substituted there instead of hydrogens. That'll make it the most stable. So if I imagine each of these options, it could come in here and push these electrons in, and so that would produce one product. Oops. One product that would look like this. Or it could pick off this proton and push these electrons in. I don't have to worry about antiperiplanar or anything once the leaving group's already gone. So I'm just imagining all the possibilities that would result from each alpha proton or H beta proton being removed. And the third option is for it to come over here and pick off that proton and push these electrons in. And so that one would give this. In terms of the wedges and dashes, wherever there was a group positioned spatially, if there's no reaction occurring there, its spatial positioning shouldn't change. So that's why these are still solid wedges. But here, when I remove this proton and these electrons swing in to make a pi bond here, these two carbons are both now sp2. And so there's no three-dimensional solid or dashed wedge there. So which product would be the major product? Well, it would be the one where the double bond forms during the transition state with the most carbon groups substituted on it versus hydrogens, because that's more stable during the transition state and it's more stable after it forms. It's favored thermodynamically and kinetically. So this would be the major product, and this would be minor, and this would be even more minor because of the extra protons substituted on that double bond versus carbon, or the more stable structure that has all the carbons there. So what's also happening here, though, is the water is picking off this proton. So I'm also getting an H3O+. So what's the net reaction? I've got this alcohol. Let's just call this ROH, just to save a little drawing time. All of this branched crazy structure is just R, and it's bonded to an OH group. I'm starting with that. I'm adding H3O+. That's my reactant. In the end, I'm producing this alkene. That's my major product. So we'll just focus in on that one. And what else am I producing? I'm reproducing H3O+. Oops. I also have a water leaving group that left. So I can show that also as a product in the net reaction. So as far as the net reaction is concerned, the H3O+ that I started with cancels out what's formed. But overall, I am going from one reactant to two total products. That's why I want this process to be in a concentrated solution. In this case, water is a product. And by Le Chatelier's principle, if I have a diluted solution, which means I've got lots of extra water as my solvent, that's only going to shift the equilibrium back to the other side. If I add a product, it'll shift the equilibrium back. If I remove the product, it'll shift the equilibrium forward. So that's why I'm using concentrated sulfuric acid. I need the H3O plus to make this leaving group a better leaving group so it can leave and get through the mechanism, but I want to have as little water as possible so it doesn't push the equilibrium back and shift it back toward the reactant side. So that's the mechanism we're dealing with here. Right, so the same thing would happen here. The H would be picked up by water. It'd be concentrated though, so I don't have a lot of water. That would produce H3O plus. This oxygen would pick up proton up off the H3O plus. It would make a good leaving group. That would produce a carbocation. Then the HSO4 minus is not a very good base, or nucleophile, so it's not going to do anything. What's going to happen is a water is going to pick off this proton here and push electrons in to make this product, or it could pick off a proton here and push electrons in to make this other product. And as we said, the more substituted your double bond is with carbon groups versus hydrogens, the more stable it is. So almost all the product is formed through the more stable transition state, giving me the more stable product. So in this case, it's really hard to form the other one, because once the carbocation forms, the only thing affecting where the base is going to pick off a proton is how stable is that double bond as the double bond starts to form. Why do I have a high temperature here? Well, in part, that's to facilitate the transition states, so to help the collisions occur. But it's also important thermodynamically. As we said, in this reaction, I'm going from one reactant to two products. Water is forming. Right? I'm eliminating the OH, and I'm eliminating a beta hydrogen, and those form water. So in an elimination reaction, if I go from one reactant to two products, that's a positive increase in entropy. There's more variety when the substances are free to move around independently. And so if I increase the temperature, this negative term will become more negative, and it will make the process more negative, more spontaneous, more product favored. So even when it reaches equilibrium, the increased temperature helps to shift the equilibrium toward the product side. And the fact that I'm starting with very little water means I don't have excess water shifting it back to the other side by Le Chatelet's principle. Similar situation here. Here I would have the oxygen, again, pick up an H3O plus from the water, pick up a proton from H3O plus to make a water leaving group. When that leaves, I'd get, in this case, a secondary carbocation. Once the carbocation forms, it might remain in solution for a little while before water comes along to pick off the beta proton. So now there is the opportunity for a single bond to rotate. Which would give me an alternative rotation. It's not as stable of a rotation though, because now I've got these groups kind of close together creating some sterics. So that rotation would greatly favor this side over here. So most of the product would form, 75% in this case, from a beta proton being picked off from the more stable rotation, giving me the trans product where the crowding groups aren't close together, creating instability. But once in a while, the proton would be picked off to form the double bond with those two groups on the same side, and that would be less stable, so that's why I don't get as much of it. So it's disfavored thermodynamically, and it's disfavored kinetically, which is why it's the minor product. But the difference associated with this sterics is not a major difference. And they don't have to be in the exact same plane, eclipsing, creating torsional strain for this to happen. So they can end up on the same side even though they're not creating torsional strain in the transition states. So the transition states for these two options are pretty similar. Alright, so that leads us to the second quiz question. So this is a fairly detailed mechanism. So what's going to happen here, I'm using concentrated sulfuric acid. So the fact that it's concentrated, I'd probably also use some heat. Little capital delta indicates heat. The concentrated sulfuric acid really means I have H3O plus and very little amount of water, mostly H3O plus. And so that H3O plus is going to donate a proton. Pick up a proton, electrons stay behind. That makes my OH into a good leaving group. That's the whole point of adding the acid. It's a catalyst. It gets the reaction started by making the OH into a better leaving group. Then it can leave. Once it leaves and creates a carbocation, I always, whenever I see a carbocation, I always want to consider the possibility of rearrangement. And there are actually two possible rearrangements here that are both reasonable. This hydrogen here could shift over, and that would go from a secondary, less stable carbocation to a more stable tertiary one. Looks something like this. Or the hydrogen here could shift over. And so that would give me a different tertiary carbocation, which would also be more stable than the initial secondary one that formed. And so either of those are reasonable. Once the carbocation forms, the OH could come back in, but then it would probably fall back out and reform the carbocation. So since I also have heat, I'm driving this toward the side with more entropy, as we said, and that involves the elimination, right? If a water comes in and picks off a beta hydrogen here or here, and the electrons swing in, the water picks that up. It doesn't connect to the structure. It remains an independent structure with its greater entropy. So I would have a water, and it could pick off either this proton and swing these electrons in, which would give me a structure that looks like this, where now my double bond's forming in this position here. And I still have a methyl group here. And I still have a methyl group here. Or the water could pick up this proton and swing those electrons in. So that would give a different regiochemical outcome. The double bond's not forming in the exact same spot. Now it's forming over here. If I were to convert those into flat looking rings, which probably makes it a little easier for me to see everything, I've got one methyl group with an up here, so that would have a solid wedge. That would exist in both structures. The next carbon in this structure has a couple hydrogens, and then the next carbon over is where the double bond starts. Up here, the next carbon over is right where the double bond starts. So now the double bond is there. And over here on the other side, I've got a methyl group pointing down. So what's the relationship between those two structures? I was thinking about this before. I was definitely thinking that they were different. So in order to determine the relationship, I'd need to get the double bond in the same spot. So if I took, say, like this structure and flip it over like a pancake, like take the right hand side, flip it up over the top, and bring it down over here, and take the other side and flip it under, that actually would give the same structure. So these two are actually identical. I think I may have told a couple people differently when looking at the quiz questions earlier, so I apologize for that. But these two should produce the same structure because if this group that's pointing away here were to be flipped over, it would then be pointing out at me. And so this methyl group would line up with that one when I flip the structure over. This one would rotate underneath and line up with that one when I flip the structure over, and the double bond would line up on that double bond if I flip the structure over. So those two, by pancaking, look identical. So there'd be more structures though, because I've got the other carbocation and I still have a water molecule that could act on it. And so there, for this carbocation, there's a proton here that could be picked off and make the double bond in this position. So I would have my double bond here. Everything else on the structure would be the same. Or there's a proton here. So if the water were to pick that proton up and swing the electrons down here, I get the double bond in a different position. Right here. So I still have this methyl group there, and this methyl group here, and this methyl group here. So what would those look like if I drew them flat? So here I would have this methyl group still here in this up position. I would have 2 carbons away, another methyl group in an up position, and then this double bond on the next carbon, and this methyl group here. So notice the methyl groups I'm drawing on the double bonded carbons are all flat, right? That's because they're all sp2 and all those atoms are in the same plane. If I were to draw this one here, we'd also have the methyl group pointing up, the same spot. This methyl group is pointing up here. But here I form the double bond over here. So what's the relationship between those two structures? Well, those two are not identical. If I try to pancake one, so the double bond of this one will line up on that double bond, by pancaking the structure and flipping over, the solid wedges, the groups that are pointing out at me, will end up pointing away. So these two won't be superimposable. And so these two are, let's see, are they diastereomers or enantiomers? If I rotate that around, they'll end up being stereoisomers for sure. If I flip this one over, if I do a pancake flip on it, it would look like this. So these would become dash wedges. The double bond would flip here, and I would have my methyl group, still here. Because I'm flipping around this axis. So what's the relationship between this structure and this structure? Well, it looks like they have the opposite configuration at each of the two chiral centers. So I believe that these two look like they're enantiomers. So even though these two are the same, these two are different. So I would produce 1, 2, 3 total products from this reaction, which is a mess. If I only want to produce one of these and I'm producing 3, that is not ideal. I'd have to somehow remove the other 2 and isolate the one I'm interested in. And especially when 2 are enantiomers, they're going to have very similar properties. I have to use some kind of chiral resolution or chromatography to separate them. It's going to be really very difficult. Alright, so let's look at some complete E1 mechanisms. So as we said, the E1 is very similar to the SN1 in terms of the mechanism. The only thing is what happens at the end, right? So there may or may not be a proton transfer to make an OH into a better leaving group. There will definitely be a loss of a leaving group, and then that will form a carbocation, which I always want to make sure I think about the possibility of rearranging. But then the difference is in the SN1, there's a nucleophilic attack, and then maybe another proton transfer. So these ones in blue are all possible, but not necessary. Once the carbocation possibly rearranges here, the last step would be a proton transfer in an E1 though, because that would give me the double bond. So here's a couple examples. Got a nice tertiary carbon here, but my leaving group's not very good. So I add concentrated sulfuric acid, that produces H3O+. The H3O plus donates a proton, leaving group leaves, I get a carbocation, I look for the possibility to rearrange, it can't rearrange, and so I expect the best base around, which is water, to pick off a proton and produce a product. This water could also just come back in here and go back, right? So that's why each of these steps is reversible. I'm doing an equilibrium, and if I want to force the equilibrium toward the product side, which also involves water as a product, I can increase the temperature to make delta S, the delta S term, larger and making delta G more negative, favoring the products more. And I can also make sure I don't use a lot of extra water, because that as a product would just shift the equilibrium back toward the other side. Why is the first proton transfer step necessary? Because OH is bad. It's a bad leaving group. I need to make it a better leaving group if I expect it to leave and produce a carbocation in the mechanism. Here I've got a different example. Here I've got a good leaving group. So if I gave you one like this, the heat helps me to realize that I'm doing an elimination, because in addition to the chloride leaving and the water picking up a proton, I'm going to get this substances as my products. I do have a water here on this side though, so I'm going from 2 reactants to 2 products, or 3 products, so there's more entropy over here, and heat will always shift the equilibrium to the side with more entropy because of the way the sign for delta S works in that equation for delta G. So that's mainly here to shift the equilibrium to the product side. But if I already have a decent leaving group, that can leave, creating carbocation. Anytime I produce carbocation, I want to look for the possibility of a rearrangement. Since this one's on a secondary carbon, rearranging to a tertiary carbon makes it more stable. So going from a secondary to a tertiary is pretty much always going to happen. It's intramolecular. Almost any collision that occurs here will have the energy necessary to shift this cloud of electrons over here to put the methyl group on the neighboring carbon and make the carbocation more stabilized by induction and hyperconjugation. Then at this point, there's hydrogens on either side here that could be picked off. There's a hydrogen here that could be picked off. But the hydrogen that leads to the more substituted double bond is going to produce the major product. So unless I ask for minor products, you don't have to draw them. Unless I say draw all the products and rank them or something like that, you would want to focus on just the major product usually, which proton allows electrons to swing in and form the more substituted double bond that's more substituted with carbon groups. That should be the major product. There's another example here. Again, we have a poor leaving group, so we need the H3O plus, concentrated sulfuric acid, or phosphoric acid, H3PO4 also works to protonate that. Once it leaves, we want to look for the possibility of rearrangement. So I've got a methyl shift here to make the carbocation more stable, and then the water would pick off whatever proton gives me the more substituted carbon-carbon double bond as my major product. The heat helps shift equilibrium toward the entropy favored side. It also helps kinetically to facilitate the collisions and give the energy necessary to get to the transition states. The maximum number of steps typically in an E1 is usually going to be 4. In an SN1 it might be 5, but 4 steps is usually the most you're going to see. And I might ask you to draw a reaction coordinate diagram for this. So we've got one here on the next slide. So let's take a look and see if we can make sure we understand why the reaction coordinate diagram looks the way it does. So what's happening here? The first step's a proton transfer. So initially I've got a positive on an oxygen, and then I form a positive on an oxygen again. Those are going to be similar in stability. When I have a positive or negative formal charge, though, I want to consider the atom that carries it, the resonance, all that's the same between these two. The only difference is this one's carrying this bulky group. And so that's going to block the solvent from coming in and forming attractions here. So this positive is not going to be quite as stable as the other one. If a positive or negative charge can be stabilized through solvation, it'll be a little bit more stable. So that's why the reactant with H3O plus is a little bit more stable than the first intermediate that has the positive on a branch structure that won't allow solvent molecules to come in and stabilize it quite as well. So the first intermediate is a little bit less stable than the reactant. That loss of the leaving group is going to be your slow step. Anytime you form a carbocation, it's pretty much always going to be your slow step, especially if it's not the most stable carbocation in the world. So forming the secondary carbocation, that goes through the slow step. That's the higher transition state than any of the other transition states. And so that's slow step. That produces secondary carbocation, which is the most unstable intermediate. Once the methyl shift occurs, it makes the carbocation a little bit more stable. So that has a low activation energy. That happens really quite quickly. As we said, almost any collision will supply the energy necessary to shift that over and give the tertiary carbocation. Then, since that carbocation is really still quite unstable, when the water picks off this proton and the electrons swing in to make the double bond, that's going to make the product. So whether the product is more stable or less stable than the reactant, that depends on temperature, right? We have an equilibrium here. The H3O plus is regenerated, and I'm producing a water as a side product. So if I'm looking at the equilibrium between the reactants and the products, right? Looking at all the steps is kinetics. And which step's the slow step, the mechanism, the rate, all that's kinetics. If I'm interested in the thermodynamics, I'm interested in comparing the reactants versus the products and trying to determine how to shift it, the equilibrium to one side or the other, or something like that. So as we were saying, heat will shift it toward the product side because there's more entropy on that side. That will give me a more negative delta G. So delta G here would be negative, specifically when I use heat. I could take advantage of the Chatelier's principle or cool it down. So if I dilute it with water or cool it down, that would shift it back to the other side. Because water is a product, adding more of that would shift the equilibrium back toward the reactant side, and cooling it down would actually change these energies. Lowering the temperature might increase the energy here and decrease the energy here, and then I would end up getting a positive value for delta G. Right? So the way the equation for delta G works, if I have the system at a higher or lower temperature, this term in the equation gets larger or smaller. And since delta S is positive, going from reactants to products, lowering the temperature means that delta G is going to depend more on the sign for delta H. So what do I expect the sign for delta H to be? Well, if I have a bunch of sigma bonds, which are more stable, and then I form a pi bond, which is less stable, I expect delta H to be positive. So that's why delta G might be positive at low temperatures when this term isn't very significant, because I'm going from a more stable, lower potential energy sigma bond to a less stable, higher potential energy pi bond. So there's a lot of detail there in the kinetics and the thermodynamics. And so try your best to master as much of it as you can before next week's exams. Alright, so in this particular example, I might ask you to predict minor products and rank their likelihood of forming. So just to point that out, in this reaction, if this oxygen picks up a proton from the acid to create a leaving group, and then it leaves, what's it going to produce? It's going to produce a secondary carbocation. So it's possible that a water might come in here, since it's a solvent, and be the first thing to collide. It might collide right here and push electrons in to form a double bond. But why is that going to be a very minor product? Well, because when the carbocation forms, it's much more likely to undergo rearrangement, because any collision with a little bit of energy can shift that methyl group over, versus to make the pi bond, the water would have to collide very specifically with that particular proton to shift electrons in and make the pi bond. It's just not as likely of a collision. So the shifting over, the methyl shift there, I don't know why I drew that. I'm going to redraw it over here. Once the methyl shifts, I would get the carbocation over here. Then the major product results from water picking up this proton, right? Why will the water come in and access this more sterically hindered proton most of the time despite the sterics? No, that's because when the electrons swing in, I get a pi bond that's more substituted with carbons. It's a little bit more stable. But when that carbocation forms, these 6 hydrogens are more sterically available, and so if the water were to collide with any one of those 6, it could push electrons in to make the pi bond here. Oh man. So it's not as stable as the other product, and it won't happen as often as the other product, but because there are so many options for the collision, and there's a little bit less sterics in each one of those options versus the option here, it is still a significant product. So what you want to recognize here in this situation is, and anytime you're doing an E1, the most major product will be the one with the most substituted carbon-carbon double bond that's substituted with carbon group specifically. The main minor product would be where if there's a carbocation rearrangement that can occur, that occurs, and then I get the less substituted double bond. And a very minor product would be one where the double bond forms without a rearrangement occurring, because the vast majority of the molecules will undergo a rearrangement before either nucleophilic attack or proton transfer in the case of an E1. Okay, so let's look at a couple of complete E2 mechanisms. So we said last time the main difference between E1 and E2 experimentally, or as far as the reaction conditions go, is the strength of the base. So what we said is, if we have a strong base, something that's fully negative and really needs to share its electrons, like an OH or an OMe or an O-terbutyl, something that's a nice strong base, it's more likely to come in as the leaving group leaves and form the double bond right away. So will this involve a proton transfer prior to elimination? Maybe, but not very likely. What's the reason for that? Well, the proton transfer prior to elimination would be necessary if we had something like this, like if our leaving group were like an OH and it wasn't a good leaving group. Normally we would try a proton transfer to make it a better leaving group. You can't do that if I'm using a strong base. If I'm trying to promote an E2 and I'm using a strong base to pick off the beta proton to push out the leaving group, if the leaving group is converted into an H3O+, I know that looks really sloppy, I want to redraw it. If I have an OH here, and I want to try to make this a better leaving group by protonating it with hydrogen and making it positive, if I add the strong base, then my hope is that the strong base might pick off this beta proton, but it won't. It will just pick off this proton. I can't use an acid to make my leaving group a better leaving group if I'm just going to put a base in there, because the base and the acid will just react together. So what do I need to do here? I need to use a different way to improve the quality of the leaving group. So if I want to promote an E2 here, and I have an OH, what I'd want to do first is to use the tosyl chloride and pyridine we talked about a couple lectures ago. That will convert the OH into a tosylate leaving group. We're going to see a lot more examples of this later. That doesn't have a proton. So if I use a proton to make a water leaving group, the base would just pick off that proton instead of doing the elimination I want. The tosylate leaving group is a great leaving group because it will stabilize the negative charge it leaves with through resonance, but it doesn't have a proton. So then I can add a strong base. Now I don't have to worry about the base messing around down here. It's only going to pick up that beta proton, push electrons in, and push out the leaving group. So I can do the elimination. So there is a way to make a poor leaving group into a better leaving group if you want to promote an E2. It's just that you can't do it with acid because the base you're using to promote the E2 will just react with the acid instead. So typically, instead of using an OH and then converting it into a tosyl group, which would work fine, it's more common to try to just use a halide as your leaving group, because those are great leaving groups already, right? They don't need acid or anything added to them. They'll usually just leave. And so then I want to look at the base. Is it a strong base? Is it a weak base? If it's a strong base, because there's a full negative, then I expect it to find a hydrogen that's antiperiplanar to the leaving group, like we said for an E2, and the E2 mechanism. If I'm using a weak base, something that's neutral, then it's not reactive enough to start the process off. So the leaving group would have to leave first, and that would produce a carbocation. And now I have a problem, because there's no way for me to control whether my weak base, since it's also a weak nucleophile, comes directly into the carbocation to produce a new sigma bond, or whether it will go to the beta proton and produce a new pi bond. So the advantage here is I get two products that I can drive the reaction toward because they have more entropy, but I'm still going to get a mixture. So this is not a good option synthetically. If I'm trying to do a reaction that goes into only one set of products, I don't want to use a weak base in the presence of this leaving group, because once it leaves, I can't really control very easily where the molecule reacts. There are some molecules that will react specifically, though, as a nucleophile versus a base. So that's what we'll talk about a little bit here to finish up things today. So we're saying water is both a weak nucleophile and a weak base. There's no way to control whether it comes directly into the carbon to form a new sigma bond, or whether it comes to the beta proton to form to push electrons in and form the pi bond. But there are some substances that will only act as a nucleophile, and others that will only act as a base. So we'll want to learn about that so we can control these reactions. So if I want to control or predict whether a reaction is going to do a substitution or elimination, there's some factors that are involved and some substances we can use to try to control that. The main thing is, what is the function of the reagent? Is it a base, or is it a nucleophile, or is it both? If it's a base, which we're going to talk about, it's probably only going to do elimination. If it's a nucleophile, it's only going to do substitution. If it's both, I'm going to get both, and that gives me a mess. It gives me a variety of different products, and then I have to separate them from one another. It's a big pain. I don't want to have to deal with that. So we're going to talk about these factors and how to predict the mechanism and predict which product we produce based on some of the experimental conditions that would be used. And we always want to make sure we keep track of the regio and stereochemical outcomes of the reaction. So when you do some of this experimentally, what you find is when you're using an oxygen, it's both a strong nucleophile and a strong base. Or if it's negative. If it's neutral, it's both a weak nucleophile and a weak base. So it's hard to control whether it acts as a nucleophile and does substitution for both of these, as well as, it's hard to control whether it acts as a nucleophile and does substitution, and it's hard to control whether it acts as a base and does elimination. So both an oxygen that's negative and an oxygen that's neutral, whether it's strong or weak, it's really hard to control elimination versus substitution in those cases. What it turns out, though, is if the element with the lone pair that's going to attack is more polarizable, which means it's a larger element, the larger electron cloud, that ends up being a situation where it's much more likely to end up sharing its electrons with a carbon and acting as a nucleophile. So we can expect whenever sulfur is involved, or a halogen or a large atom, it's almost never going to act as a base and do an elimination. So that's what we'll see on the next slide. It also has to do with sterics, though. If it's too sterically hindered, it might not be able to make it all the way in to the carbon and form the new sigma bond. So it might not be able to act like a nucleophile and attack in that situation. Right? So sterics is more of an issue when it has to attack directly into the carbon because there's these other groups that are blocking it. If it has to attack a beta hydrogen, that's not an issue because if there's sterics, the hydrogen's always on the surface of the structure, so whatever the substance is, it can usually act as a base. So sterics is an issue, but for the most part, larger atoms like sulfur, chlorine, bromine, iodine, much more likely to act as nucleophiles and do a substitution. We also know that if we want to judge whether something's going to act as a base, we can look at pKa values. Right? So we know that if a molecule has a strong conjugate acid with a low pKa for its conjugate acid, then it's going to be a very weak base. The more strongly acid, the weaker its conjugate base. And so if it's a weak conjugate base, it's not going to promote an elimination reaction. An elimination reaction requires the substance to pick off a proton. If it's a weak base, it won't do that. It'd be much more likely to come in as a nucleophile and connect to a carbon. So we can look at the pKa values to judge these two. So, for example, we know sulfuric acid has a lower pKa value than hydrochloric acid. So Cl- is a slightly stronger, I should probably say less weak. These are both very weak because their conjugate acids are very strong and very negative. If either of these were to pick up a proton to become HCl or H2SO4, they would immediately give the proton back away. So they're terrible bases because their conjugate acids are so strong and reactive. But this one's a little bit less weak, and this one is more weak. Very, very terrible base. So in any mechanism that you draw, you should not have a really weak base picking up a proton. These will always be in some solvent, and the solvent will be a better base than either of these at picking up a proton. So that's also something to look out for. In terms of basicity, we know that electronegativity plays a role. So oxygen has an electronegativity that's higher than nitrogen. And we know that nitrogen's more willing to share electrons because it won't rip them away since it doesn't have quite a high electronegativity. So we do expect both the nitrogen to be more basic and more nucleophilic, more reactive, more willing to share its electrons with either a carbon or a proton than an oxygen. So that's another factor, and the other factors of aerial are relevant as well, which we obviously don't have time to go through all of them again. So this is a really helpful slide here. It depicts one of the couple of the figures from the textbook, and so this one I would refer back to, and I would definitely keep my eye while I'm practicing on the page in the textbook that includes this graphic, which is, just grab that page for y'all real quick. This is on page 385. It's a really nice graphic here because it shows if I want to do a substitution, some of the substances that are not going to act as a base. So these are not bases. They will not really pick up protons very readily compared to how nicely they will come in and attack a carbon. So I can expect if I have any of these around, it's much more likely to do an SN1 or SN2. And if it's a strong nucleophile, well, actually, the SN1 or SN2 would depend more on the sterics where it's being attacked, where it's attacking. These substances here won't do substitution. They're pretty much only bases. So they will only do elimination. So you have to kind of get used to these and judge based on what you're dealing with, what type of mechanism you expect. So as we were saying a minute ago, when I have a negative on an oxygen, that's reactive. It's strong, but it's not really selective in terms of whether it will attack a carbon or pick up a proton. The major factor there is sterics. So the smaller the grouping with the negative, the more likely it is to act as a base. It could also act as a nucleophile though. But once I put larger and larger and larger electron clouds, it's definitely much more likely to act as a base. I think I might have misspoken here. Nucleophile. The smaller ones could be a base or a nucleophile. The smaller it is, the more likely it is to be a nucleophile though, because it can make its way into the carbon. But the larger the electron cloud, the less likely it is to be a nucleophile, much more likely to be a base because the oxygen can't make its way all the way into a carbon when it's carrying this big bulky group that's going to bump into other stuff and create repulsion during the transition state. And these are almost usually not practical because they're weak. But in this case, a neutral oxygen, again, it can attack as a nucleophile or as a base. But these are all weak. So these will usually only be E1 or SN1. They're not strong enough to get the process started, so this one will usually be E2 or SN2. Because they're stronger, they'll get involved right away in a mechanism that involves either the base or nucleophile attacking right away. The weaker ones, which are more stable, they're not going to do anything usually until the leaving group leaves behind a carbocation. Then they'll either attack the carbocation and do a substitution, or pick up a beta proton and do an elimination. And we can use temperature to help control that to an extent because there's an entropy difference between the products that result from those two mechanisms. So these two compounds here are new, and these are just acronyms. So we'll just take a quick look at those, DBN and DBU. These are their structures. And what they have is a nitrogen that can pick up a proton, but it is neutral. So normally think of a neutral nitrogen as being a pretty weak base, because once the nitrogen picks up a proton and creates a positive charge, that's a little bit unstable. The advantage that both of these have is that they're a bit sterically hindered, right? So these rings here create some sterics. So I do not expect either of these to attack a carbon and do a substitution and push out a leaving group. Too much sterics associated with the rings trying to come in and connect to a carbon. So that's why these are only bases. They're only going to do elimination, not substitution. But what makes them actually decently strong, not nearly as strong as an oxygen with a negative, but they're pretty strong bases and they promote elimination pretty well. And that is, once they pick up a proton, the positive is stabilized through resonance on each of these. So the resonance stabilization of the positive charge that results makes it more likely that they'll pick up a proton and promote an E2 elimination, or even possibly an E1 if there's a really good leaving group that's already left. Typically these are strong enough to do the E2 elimination even when I do have a good leaving group. So you want to keep that in mind as well. Like we said, for these, the main thing is sterics. The more sterics there is, the less likely it is to do a substitution, the more likely it is to pick off a beta proton that's more available and it can collide without creating a lot of steric hindrance during the transition state. So doing this avoids steric hindrance or repulsion during the transition state. And obviously if it's stronger, it's more likely to do an SN2 or E2 versus an E1 or SN1. Right? Those only really occur when I have a weak reagent, because these require the leaving group to leave first, and then the reagent only comes in after the carbocation forms. And the last category, as we said, these are weak, so we don't expect them to get involved until after the carbocation forms. They're not unstable, so they start so low in energy to begin with that only once the carbocation forms would they get involved in a collision that would maybe then, go ahead and produce a product after that. If they were to react right away with the sterics and the charges that would form, it would be a much higher energy pathway if I were to do an SN2 or E2, because of the positive charge that forms on these. It's more likely to do an SN1 or E1 because the carbocation formation goes through lower energy transition state than the one that would require these to come in and collide as the leaving group's leaving. Alright, we made it through all that stuff. Any questions about anything related to any of that? I know it's a lot of stuff. Well, there's a lot for you to practice here in Chapter 8 to prepare you for next week's exams. On Tuesday, we're going to finish up Chapter 8. That's going to be it for reactions for a little while. We're going to switch gears and start to talk about spectroscopy and spectrometry. We're going to deal with Chapter 15 and 16 starting Tuesday and Thursday of next week. And that's going to give us the ability to take molecules that we have in the lab or samples we have in the lab and get a lot of information about the structures of those molecules using different instruments and machines in the lab. So we're going to talk about that after we finish Chapter 8 next week.